Good afternoon, everyone. My name is Liwei Jiang, and I'm from the School of Integrated Circuits at Tsinghua University. It's really a pleasure to be here today to share our latest research with you. The title of our work is Flip-chip bonded dual-substrate RF MEMS switches with SOI Cantilever, which has been accepted for presentation at IEEE Sensors 2025. This project is a collaboration between myself, Zirui Liu, and our advisor, Professor Zheyao Wang. So what's the big idea here? We've developed a new kind of MEMS switches that tackles some of the biggest challenges in RF performance, reliability, and packaging all at once. In this task, I will talk you through why we started this work, how we design and build the device, what the test result look like, and where we think this could go next. Let's start with the motivation behind this project. Modern RF front ends, especially in satellite communication, radar systems, and other high-frequency applications, are demanding more and more from their components. We are talking about ultra-low insertion loss to keep signal clean, high isolation to avoid interference, and excellent linearity to handle complex modulation schemes. But here's the problem. Traditional cantilever-based RF MEMS switches, while promising, have some serious limitations. First, reliability is a big issue. Unprotected metal contacts can weld together or suffer from material transfer. And if the switch is left exposed, it's vulnerable to dust, humidity, and even mechanical shock. Second, there's what we call the packaging paradox. We can encapsulate the switch with polymers like BCB to protect it, but those materials outgas in vacuum, which makes them unsuitable for space or high vacuum RF applications. And third, there is a trade-off between RF performance and reliability. Some dual-substrate designs using glass and silicon can reduce RF losses, but they introduce TSV, related thermal stress, parasitic capacitance, and other reliability risks. So the big question we asked ourselves was, how can we achieve high RF performance, long lifetime, and environmental protection without making the device impossible to manufacture? Our answer is a dual substrate architecture that separates the mechanical and the RF functions, so each part can do its job better. Here's how it works. On the first substrate, we fabricate a single crystal silicon cantilever on an SOI wafer. It gives us low stress, excellent mechanical properties, and high repeatability. On the second substrate, we use a high resistivity silicon wafer to build the RF environment, including coplanar waveguides, gate electrodes for actuation, and insulation layers. And to bring it all together, we use flip-chip bonding with metal pillars to connect the two substrates. The result is a self-encapsulated structure that protects the cantilever from the environment. So no need for extra packaging and no exposure to contaminants. Now let's take a look at how we actually build these things. Starting with SOI side, we use a 6-step process. First, we begin with SOI wafer preparation, followed by aluminum oxide deposition. Then we do chromium and gold metallization to form the contact layers. Next, we electroplate copper pillars. This will later be used for bonding. Then we etch the aluminum oxide using the metal as a mask. No extra photolithography needed here. Then we etch the device layer using DRIE to define the cantilever. And finally, we release the structure using vapor phase hydrofluoric acid. This removes the sacrificed oxide underneath. This gives us a freestanding stress-controlled cantilever that is ready to bonding. On the second substrate, we build the RF environment. We start with a high resistivity silicon wafer, and here's what we go. First one, metal sputtering to form the base layers. Second, dielectric deposition for insulation. And the third one, copper pillar electroplating. This will align with the ones on the SOI side. Then coplanar waveguide metallization. This is where the RF signal travels. And finally, flip chip bonding to join the two substrates together. What's great about the process is that we don't need through silicon vias, no bulk thinning, and no exposure to particles, which keeps the device clean and robust. Here are some images of the fabrication device. Under the microscope, we can see excellent alignment between the cantilever and the CPW before bonding. From the SEM images, we confirm a clean undercut with no residual oxide, which is critical for proper release. The final chip is 9mm product 9mm, and it includes 4 independent switches, plus a through line for calibration. For electrode testing, we built a custom setup. It contains a network analyzer to measure S parameters, an oscilloscope to capture time domain waveforms, and a signal generator, an amplifier to drive the switch. We apply a 68 volt, 2 kHz square wave to gate to the gate. This is the actuation signal. And we feed a 100 millivolts, 20 kHz sine wave into the RF port as a carrier signal. We also use a through line reference on the same chip to de-embedded the loss from the CPW and the probes. So we are measuring only the switch performance. Here's what the dynamic response look like. In the on state, the carrier signal passes through clearly with minimum distortion. In the off state, the signal is completely isolated, no visible feed through. The pooling time is about 7.5 microseconds, which is fast compared to many thermal or hybrid actuators. And this performance remains stable over thousands of cycles. Now for the RF performance. After de-embedding, the average insertion loss across 8 switches is 0.12 decibel at 0.5 GHz and 0.68 decibel at 2 GHz. the variation is within 0.2 decibel, which shows good uniformity. We also did a statistical analysis of contact resistance across 17 fresh devices. This is what we get. Mean resistance is 1.6 ohm. The standard deviation is 0.39 ohm. The IQR is from 1.38 to 1.75 ohm. And in terms of lifetime, we've tested up to 24 million cycles without a carrier signal, and the switch is still working. So to wrap things up, we've demonstrated a dual-substrate flip-chip bonded RF MEMS that achieves low insertion loss, low contact resistance, and long lifetime. Most importantly, we've broken the traditional trade-off between RF performance and reliability. Looking ahead, this platform is fully compatible with heterogeneous integration. Since both substrates use surface-only processing, we can easily bond them with gallium arsenide, quartz, polyimide, or other RF-friendly materials. This opens up exciting possibilities for advanced front-end modules in satellites, radar, and so on. Here is a reference list. Thank you so much for your attention.